Hi, I'm Chin Kelly. My matrix number is 2115127. I'm going to explain question 1a. In the MATLAB code, the first line is actually creates an array n, where n is actually a sequence of integers starting from 0 until 82 with the increment of 1. Moving on to the second line actually creates an array x that represents the complex discrete signal given by the question, where exp is actually the exponential and 1j is actually the imaginary unit. Pi is actually the mathematical constant type. The third line, stem n, x, semicolon grid, this line actually uses the stem function to create a stem plot for the signal x with time indices n. The grid command adds a grid to the plot for a better visualization. And moving on to the fourth line, x label n, this actually labels the x-axis as n. And moving on to the last line, y label x bracket n, this actually labels x bracket n at the y-axis. And at the right side, this is the plot generated by using MATLAB. Now I'm going to explain the Python code for question 1a. The first line, import numpy as np. This line actually imports the numpy library and allows us to use this function. And for the second line, import matplotlib.py plot as plt. This line actually imports the matplotlib library and allows us to create plots and visualization. For the third line, n, this actually creates an array n using the numpy's arrange function. It represents a sequence of integers starting from 0 until 82 with the increment of 1. And moving on to the fourth line, this actually creates an array x that represents our complex discrete signal given by the question, and it is calculated by using the numpy function, where exp is actually the exponential, 1j is actually the imaginary unit. And moving on to the fifth line, plt.stem bracket n, x, this actually using the matplotlib library and creates a stem plot of the signal x with corresponding time indices of n, and the stem plot actually represents the magnitude and the phase of the complex signal. plt.x label bracket n, and this actually label n at the x-axis, and while plt y label x bracket n, and this actually label x bracket n at the y-axis. And since we are using the Google Colab, plt.show is actually replace the plot in a pop-up video in the Google Colab. And at our right side, this is the plot generated using the Google Colab. As you can see, the Python code and the MATLAB code generated the same type of plot. Moving on from question 1b, the MATLAB code for question 1b is actually more or less similar to question 1a, except that for the first line, this actually creates an array n, where n is a sequence of integers starting from 0 until 20 with the increment of 1. And for the second line, this actually creates an array x that represents the discrete signal given by the question, and this signal is calculated by using the cost function. And starting from the third line until the fifth line, this actually serves the same purpose as question 1a. And as you can see at the right side, this is the cost signal generated using MATLAB. For question 1b, the Python code is also more or less similar to question 1a, except that at the third line, this actually creates an array n using the numpy's arrange function, that it represents a sequence of integers starting from 0 until 20 with the increment of 1. At the fourth line, this actually creates an array x that represents the discrete signal given by the question, and this signal is calculated by using the cost function. And starting from the fifth line until the last line, this actually serves the same purpose in question 1a as I explained earlier. And at the right side, this is the cost signal generated using the Google Colab. And as you can see, the Google Colab plot and the MATLAB plot shows the same, and this proves that the Python code is correct. For question 1c, the MATLAB code is also more or less similar to the previous question, except that at the second line actually creates an array h that represents the discrete signal given by the question, and the signal is calculated using the sine and cos function. And at the third line, stem bracket n, h, semicolon grid, this actually creates a stem plot of the signal h with time indices n, and similarly, the grid command is used to add it to the plot for a better visualization. And for the fourth line, x label bracket n, this actually label n at the x-axis, and the last line, y label bracket hn, and this actually labels hn at the y-axis. At the right side, this is the signal generated by using the MATLAB. The Python code in question 1c is also more or less similar to the Python code in the previous question, except that at the line 4, this actually creates an array h to represent the discrete signal given in the question, And this signal is calculated by using the numpy sine and cos function and the specified mathematical expression. And starting from the fifth line until the last line, all these lines actually serve the same purpose as the previous question. And at the right side, this is actually the plot generated using the Google Colab. Question 1D actually shows an impulse signal. In the MATLAB code, the first line actually creates an array n, where n is a sequence of numbers starting from -5 until 5 with the increment of 0.5. Moving on to the next line, this actually creates an array impulse 1 to represent the impulse signal at n equal to -3 that sets the value to n when n is equal to -3 and 0 when at others. And similarly, at the third line, this actually creates an array impulse 2 to represent the impulse signal at n equal to 4 and set the value to 1 when n is equal to 4 and 0 at others. Moving on to the fourth line actually creates an array h that represents the discrete signal given in the question. This line actually combines two impulse signals to create the signal hn. And moving on to the fifth line, stem bracket n comma h bracket semicolon create. This actually creates the stem plot of the signal h with time indices n. The Greek command is added to the plot for a better visualization. X label bracket n, this actually label n at the x-axis. Y label bracket h bracket n, this actually label h bracket n at the y-axis. And at the right side, this is the impulse signal generated by the MATLAB. For question 1D, this is the Python code. At the first line of the Python code, it says that import numpy as np. This actually imports the numpy library and allows us to use its function for numerical operation. And moving on to the next line is import matplotlib.py.stlt. This actually imports the matplotlib library and allows us to create plots and visualization. Moving on to the next line, this actually creates an array n using numpy's arrange function. It represents a sequence of numbers starting from -5 until 5 with the increment of 0.5. Moving on to the line 4 actually creates an array impulse 1 that represents the impulse signal at n equal to -3. The n.np.where bracket n equal to -3, 1, 0. This actually sets the values to 1 when n is equal to -3 and 0 when it is at others. And similarly, impulse 2 is actually an array to use to represent the impulse signal when n is equal to 4. And np.where is a function to set the value to 1 when n is equal to 4 and 0 at others. And moving on to the sixth line actually creates an array h to represent the discrete signal given by the question, and it is calculated by subtracting the impulse 2 from 2 of impulse 1. And as a result, h has the value of 2 at n equal to -3 and -1 at n equal to -4 and 0 at others. Starting from plt.stem bracket n comma h until plt.show bracket, this actually serves the same purpose as the previously question. And at the right side, this is the discrete signal shown by the Google Colab. It is, as you can see, this is an impulse signal.
Good day, Doctor. I'm going to talk about question 1e. For MATLAB code, I set n equal to 0 to 20 in interval of 1. I let a1 equal to un, a2 equals to un minus 10, and a3 equals to un minus 20. I set a1, the amplitude from 0 to 20 is equal to 1 using the 1's functions. While for a2, I set amplitude of n from 0 to 9 is equal to 0 using the 0's function, and amplitude of n from 10 to 20 is equal to 1 using 1's functions. And for a3, I set amplitude of n from 0 to 19 is equal to 0 and 20 is equal to 1. Then I type up the equations that given from the question, and I'm using the figure functions to display out the graph that we wanted, and using the stem function to plot out the graph, and with grid and x label for x-axis of n and y label for y-axis of yn, and title is Q1A. So for the Python code, I import necessary libraries, imports the numpy library and renames it as np, and imports the matplotlib library and renames it as plt. Then I create an array n using np arrange functions that contains values from 0 to 10 with step of 1, and define 3 unit step sequence using the numpy web functions. Un represents unit step sequence that is 1 when n is greater or equals to 0, and un minus 10 represents the unit step sequence that is 1 when n is greater or equals to 10 and 0 otherwise, and un minus to 20 represents a unit step sequence that is 1 when n is greater than or equal to 20 and 0 otherwise. I type out the given mathematical expression and create a stem plot using a matplot library. I also create line stem plot of the sequence yn using the values from n and y array. The use line collections equal to true arguments ensures that line collections are used to represent the stems. Besides that, use the PLT functions to add a grid, labels, and title to the plot. And then the PLT show command will display the plot to the user. So this is the proven part, is the math calculations part that I've done. So to understand how to form out the MATLAB code and Python, we need to understand how UN looks like. For UN function, from n equals to 0 and above is equal to 1, and un minus 10, n equals to 10 and above, it is 1, but below 10, it is 0. For un minus 20, when n is equal to 20 and above, is the un minus 20 is equal to 1, and but n equals below than 20, it is 0. And from that, we can do the calculation. un minus 10 will draw out the figure that I shown. Okay, you still need to plot out the signals un minus 10 minus un minus 20, and you will draw like I do in this slide, combining the graph you have drawn, calculating it from n equals to 0 to 20 with the equation provided from the questions. Eventually, you will form out a graph like I do of yn in this slide I'm shown here.
Good day, doctor. My name is Jodoli. My matrix number is 21115127A. I'm going to explain question 2a and b. The question 2a is 2x bracket n minus 5 bracket minus 3x bracket n plus 4 bracket. First, we define the vector n from 0 to 12 with the increment of 1, and then we define the signal x with the given values, which are 1, 2, 3, 4, 5, 6, 7, 6, 5, 4, 3, 2, 1. Then we set the maximum shift variable to 10. We pen the x vector with zeros at the beginning and end to account for the maximum possible shift. Next, code able to calculate the signal yn by taking two circular shifts of the padded x signal. The first shift is 5 position to the right, and the second shift is 4 position to the left since it is negative 4. These shifted signals are scaled by 2 and negative 3, which will subtracted from each other to obtain yn. Next, extend the n vector by adding a range of values before and after the original n vector. This effectively increases the range of n to account for the shifting of the signal later. Last, we plot the yn signal by using the stem functions and set the labels for x-axis and y-axis of the plot. When running this code, you will get a stem of plot of yn as a function of n, where n has been extended to account for shifting. And yn is calculated based on the circular shifts of the original xn signal. The result will show the effects of circular shifting and scaling on the signal. Here's the Python code for question 2a. First, we import the libraries SNUMPy, SNP used for numerical and array operations. Matplot library.pyplot imported as PLT used for plotting graphs. We define n as containing values from 0 to 13 and define the signal x as a NumPy array with values 1, 2, 3, 4, 5, 6, 7, 6, 5, 4, 3, 2, 1. Then we set the max shift values to 10. This values is used for circular shifts and zero padding. The function np concatenate is used to add zeros at the beginning and the end of the x array. Next line, calculate the circular shifts of x with different offsets and apply the given coefficients. Define the range n with adjusted values to match the shifted and zero padded x. Lastly, we use PLT stem to create a stem plot of n and y. The use line collection equals to true argument is used to improve performance for stem plots. Then we add grid lines to the plot by using plt.grid. Then label the x-axis and y-axis by using the plt-x label and plt.y label respectively. Finally, display the plot by using the plt.show bracket. Question 2b is similar to the question 2a. The question is x3 minus n plus with xn multiplied with the xn minus 2. The only difference is this question's adding the convolutions and the new function flip, which I will explain later. First, we define the n from 0 to 12 with the increment of 1 and set the signal x with the given values, then set the maximum shift to variable 5. Then extend the end by using these sentences of code to add a range of value before and after the original end, and pads x vector with zeros at the beginning and the end to account for the maximum possible shift. The y2 is the circular shift, the x signal 2 position to the right, then using the function flip to flip the x vector from left to right to form the z. At this part, we finished to solve the back part of the questions xn multiplied with xn minus 2. Next, we set the sum maximum shift to variable 5 and repeat the step to adjust the range of n and z. And y1 is the circularly shifts and flip of z signal 3 position to the right. And next code y3 equals to convolution x y2 is used to perform the convolution between the original x signal and circularly shifted y2 signal. Then concatenates the y1 with 12 zeros and then add y3 to obtain the final signal y. Finally, we're using the stem y, create x label, y label to create the graph. Here's the Python language for question 2b. Every time we write our code, we need to import our libraries, then we can run our functions. Same as question 2a, we need to set the range of n, define the signal x, and set the maximum shift of the variable 5, then extend the range of n with the maximum shift. After maximum shift variable, the left will become 0 after setting. Now, y2 equals to np.row bracket x, 2 is the function of circular shift of x signal 2 position to the right. Then flip the x vector from left to right to form the z. Then repeat the step to adjust the range of n and z. Then y1 is the circular shapes and flip of z signal 3 position to the right. Then the np.convol function is the convolution called in Python language. It performs a convolution between the original x signal and the circularly shifted y2 signal. Last, store the result in y3. Then the next 3 sentences of code is used to ensure the y1 and y3 have the same length by truncating the longer ones. Then the circularly shifted signal y1 and the convol signal y3 we will be adding together to obtain the final signal y. Then update the array end to include the appropriate range for the plotting the stem plot. Last, to create the graph, we're using the function plt.stem, and the parameter use line collection equals to true is used to address a deprecation warning. And the x label, y label is used to label each axis with n and y n respectively. And last, display the stem plot by using the function plt.show.
Hi, Wendy, with metric number 211151362, would like to explain for question 3. For this question, we have to find the xn by determining un minus un minus 12. As we know, un is a unit step signal where the amplitudes will be 1 from n equals to 0 until positive infinity. For simplicity, I set the range of n for minus 12 to 12 with an interval of 1. And we assume these two signals consist of 1 row and 25 column, which is from negative 12 until 12. We use the function zeros and ones to plot these two signals. First, we plot un as x1 with zeros 1, 12, where the amplitude is equals to 0 from n equals to 12, negative 12, until n equals to negative 1, which is from the column 1 until the column 12. And for ones, we have 1 and 13. The amplitude is equals to 1 from n equals to 0 until n equals 12. We will subplot this signal as 5.1. For un minus 12, we plot it as x2 with zeros 1, 24, and ones 1, 1. And the step is same as the previous un. We will subplot the signal as 512. In this case, we use stem function to produce the discrete signals. The Sn can be found as we minus x2 from x1. After that, we have to get mirror side of xn, which is x minus n, in order to determine the even and odd part of xn. We use the function flip_lr to flip the signal at y-axis to get x minus n, and we will plot it as y. For the even part, the formula used is xn add with x minus n divided by 2. So in this case, the even part will be x add with y divided by 2. Meanwhile, the odd part will be x add with y divided by 2. And finally, we will subplot all the signals produced in figure 1. And these are the graph and the signals that we generated using our MATLAB code. First, we define the range of n from negative 13 to 13 using the np arrange functions. Then we generate the unit step functions, un using the np where function. And this function is used to create an array based on the condition. For unit step, the amplitude equals to 1 from n equals to or greater than 0. So the condition of this array will be n greater than or equals to 0. When n greater than or equals to 0, the condition will be true. So the corresponding element in un array will set to 1. When n is smaller than 0, the condition will be false. So the corresponding element is set to be 0. Same goes to the signal of un minus 12. The n equals to or greater than 12 will be set to 1, otherwise will be set to 0. Now we can find the xn by minus un minus 12 from un. In order to obtain the even and odd part of the xn, we must obtain the x minus n. First, we flip the xn horizontally using the np flip_lr function, but the origin of this flipped xn is not at 0. So we have to shift the x minus n to the right by one step using the np row, so that the origin will be reset to 0. Then we can determine the even part and odd part of the xn respectively. The even part can be obtained by xn plus x minus n times with 0.5, or we can divide it by 2. Meanwhile, the odd part can be obtained by xn minus x minus n times with 0.5. Lastly, we plot each of the graph of un minus 12, xn, flip xn, x minus n, even and odd part of the xn. So this will be the final result of our graphs. As we can see, the result is same if compared to the graph generated using the MATLAB. And that's all for question 3. Thank you. For question 4, we have to determine the LTI system response with the input xn and impulse response hn. First of all, for signal Sn, the amplitude for Sn is 2, 13, 4, 0, -1, -4, and -2. We set the n range from -3 to 3 with step 1, so that the origin will be at 0. We plot Sn as discrete signal using the signal function and subplot it with 3, 1, 1. For impulse response Hn, also, we set the n range from -4 to 7 with step 1 so that the origin of this signal will be at 3. We also plot Hn as discrete signal using the same function and subplot it with 3, 1, 2. In order to find the LTI system response, we will use the convolution method as every LTI system can be written as a convolution product. So in this case, the convolution function is used. We convolute the Sn and Hn using convolution function and plot it as y. The n is set from -4 to 7 as this is the maximum and the minimum range of n to move the Hn. The result of convolution will also be shown in a command window. And these are the final graph produced. Moreover, I also use method 2, which is tabular method for this convolution. Same goes to this method. We also plot xn and hn, same as the previous method. We plot the xn and hn by using the same function. The tabular method performs the diagonal addition between the xn and hn. First, we will create a matrix and define it as Z using for loop. Then we will write the nested for loop to perform the diagonal addition. The R represents a row and C represents column. The K equals to R plus column, the matrix Y, and initialize CB as 0. For R less than or equals to K, the addition will be operated for this loop. After a round of addition, the T will plus 1 and the Y will be stored in the series. After that, the CD will be defined as 0 again. And finally, we will display the Y in a command window and subplot it in figure. And this is the final result, as we can see from this figure 1. As you can see, the result is same as using the common convolution functions. I also use the tabular method handwritten to prove the diagonal addition between the xn and hn. And now I would like to explain the Python code for question 4. In this question, we have to find the response of an LTI system. First of all, we plot the Sn using the NP array for 2, 13, 4, 0, -1, -4, and -2. Then the n of the xn is set from -3 to 4, so that the origin of xn is at 0. Next, we plot for hn. We're using the same NP array for 2, 3, 0, -5, 2, 1. We set the n for hn from -1 to 5, so the origin will be placed at 3. Now we can perform the convolution to obtain the yn in full mode using the NP convol. In full mode, the result of convolution will have both positive and negative indices to capture the entire convolution result. So here we can see this is the entire convolution result from the xn and yn. Lastly, we subplot the xn, hn, and the system response yn for 311, 312, and 313 respectively, and these are the graph generated using Python. The result is same if compared to the graph generated using the MATLAB. That's all for question 4. Thank you.
Okay. For array n contains values from -3 to 3. Array X have given number from questions. The code then set up a subplot with 3 rows, 1 column, and selects the first subplot for the subsequent plotting using the subplot 3, 1, 1. Then create a stem plot of signal X against the values in n. Grid adds a grid to the plot, and the title X label and Y label are used to label the plot appropriately. It generates a random number R using the RADN functions. This random number will be used for adding noise to the signal later. Makeshift number is set to 3, and the code updates n to include a wider range by subtracting makeshift number from the minimum value in n and adding the makeshift number to the maximum value in n. This step is to prepare for shifting the signal later. A new array A1 is created by adding zeros to both sides of the original signal X to accommodate shifting. The number of zeros added is determined by the makeshift number. The code circularly shifts the signal A1 by 2 positions using the shell shift, and this simulates a time domain shift in the signal. The shifted signal A1 is combined with the random noise R to create a new signal Y. The code then sets up a new subplot to plot the signal Y against the updated values of n, and similar to the first subplot, it adds grid lines and labels. X correlations functions used to compute the cross correlation between the original signal X and the shifted noisy signal Y. The resulting cross correlation sequence is stored in Z, and the corresponding legs are stored in legs. Finally, a third subplot is set up to plot the cross correlation sequence Z against the legs, and grid lines and labels are added to this subplot as well. Import necessary libraries: NumPy and Matplotlib library pilot. Create an array n to represent range of the x-axis. and it spans from -3 to 3 in this Python code. Define an array X to represent the signal xn. This is your input signal with specific amplitudes at different time indices. Create a new figure for plotting with a specified size of 8 units in width and 6 units in height using the PLT figure. Fig size equal to 8, 6. Plot xn in the first subplot and use the plt.subplot311 to specify that you have a 3 times 1 grid of subplot and you are currently plotting the first one. Besides that, also using the plt.stem_nx to plot signal xn at a specific time instance and using the stem plot. Add a grid to the plot using the plt.grid. Set the title, x-axis label and y-axis label for the subplot using the plt title, plt label, and plt y label. Generate random noise R using the mp_random RADN. Define a maximum shift value, max shift number, and create a new array N to present extended range for the shifted signal, which accommodates the maximum shift. This involves the concatenating zeros and both ends of the original and range. Create a shifted version of the signal times 1 by using NP row and shift it by 2 positions. Create a new signal Y by adding the random noise R to the shifted signal times 1 x1. Plot yn in the second subplot in similar manner as the first subplot. Compute the cross correlation of signals Sn and Yn using the np.correlate Sy equals to full and create an array of legs to represent the x-axis values for the cross correlation using np arrange. Shift the legs array to move a particular value 213.979 in this case to the left by a specified shift amount. Then truncate the Z array to match the length of the legs shifted array. Plot the cross correlation results in the third subplot showing the cross correlations of signal xn and yn. Finally, use PLT type layout to ensure proper spacing and layout for all subplots and use PLT show to display the complete figure with all 3 subplots. The code essentially generates and visualizes the original signal and shifted version of the signal with added noise and their cross correlation.
Good day to Dr. Lim. I'm going to continue with question 6. In the question, it requires to perform circular convolution. For both part A and B, I will demonstrate 2 methods to perform circular convolution in MATLAB and as well as in Python language. The first method is by using convolution function. First, I define the independent variable of n that starts with 0 and n at 5 with increment of 1. Then I define the input sequences xn and vn. Convolution function cconv is applied, and since both signals have the same length, which is 5, the resulting vector is specified to 5. After that, the result and graph is displayed. Subplot function is used, and stem function is used to plot discrete signals. Title, y-label, and x-label functions are defined in order to label graph title, x-axis, and y-axis. The second method is by using discrete Fourier transform. First, I define the independent variable of n that start with 0 and n at 5 with increment of 1. Then I define the input sequences xn and vn. The discrete Fourier transform function FFT is implemented in signal xn and vn. After that, inverse discrete Fourier transform function IFFT is computed by multiplying FFT of x and v. Then the result is displayed. Both methods generated the same discrete signal graph, where when n equals to 1 and 2, yn equals to 15, when n equals to 3, yn equals to 4, when n equals to 4, yn equals to 29, and when n equals to 5, yn equals to 5. The figure below shows the real number and imaginary number of the resultant circular convolution of xn and vn. This is the Python code for question 6a. First, I declare the library number, which is import numpy as np. The second library that involved is import matplot library, pyplot as plt, which is the library to plot graph. Then time interval is defined with range 0, 1, 2, 3, 4 by using function n equals to mp arrange 0, 5, 1. Next, the input sequences x and v are defined. Circular convolution of both signals are computed using DFT, where the function is mp.fft and IDFT where the function is np.fft.ifft. The result is plotted and printed. For question 6b, convolution function is used. First, the independent variable of n that start with 0 and end at 4 with the increment of 1. Then, input sequences xn and hn are defined. Convolution function ccom is applied and the resultant vector length is specified to 5. After that, the result is being displayed by plotting the graph. The second method is by using discrete Fourier transform. First, the independent variable of n that start with 0 and end at 4 is defined. Then, the input sequences xn and hn are defined. Fourier transform, which the function is FFT, is applied to both input signals. After that, inverse Fourier transform IFT function is computed by multiplying FFT function of x and h. The result is this. Both method generated the same discrete signal graph where when n equals to 1, yn equals to negative 23, when n equals to 2, yn equals to negative 69, when n equals to 3, yn equals to 35, when n equals to 4, yn equals to 105, and when n equals to 5, yn equals to 73. This is the Python code for question 6b. First, I declare the library number, which is import numpy as np. The second library that involved is import matplot library, pyplot as plt, which is the library to plot graph. The third library that involved is from math import py as p, where it is a math library defined py as p. Then time interval is defined with range 0, 1, 2, 3, 4 by using function n equals to mp.arrange 0, 5, 1. Next, the input sequences x and v are defined. In order to perform circular convolution, both input signal must have the same length. Thus, function big letters n equals to maximum length of x and length of h is declared. Next, the sequences are paired with zeros to have the same length. Then, circular convolution is computed using DFT and IDFT function. Lastly, the result is being printed and plotted.